All right, welcome back, everybody. So, last time we were here, we were learning everything we could possibly learn about ionic bonds. And it was pretty simple, right? Check out the difference in electronegativity. If it's greater than 1.7, bam, electrons transfer. Metals lose the entire valence shell. Non-metals gather them all up so that they all have 8 on the outside. That's the magical thing, is to have 8 on the outside. So, that was easy. Let's get into the part that's not. Because what happens if that difference in electronegativity is less than 1.7? Well, that's when you get some of the weirdness of weirdness, man. That's where you get a kind of bond called covalent bond. And covalent bonding is where those valence, like the valent part of the name, are shared. That's where we get the co part of the name. So we're going to dig into covalent bonds. Giddy up. So, what is a covalent bond? Well, a covalent bond is a bond formed by sharing valence electrons. Now, it doesn't say valence electrons right here, but we're all just going to assume and know that all of this, whenever we're talking about bonding, we're talking about valence electrons, right? So, the covalent, like that, means like together or sharing, and the valent, that's for valence electrons, right? And that is what happens if this tug of war between atoms, like the the pull from electronegativity, if the difference in electronegativity is less than 1.7, right? So if it is less than 1.7, what that means is no one, like neither one, is able to rip electrons off. So in that tug of war, nobody wins. So what happens is they end up sharing. So they kind of like, the electrons literally kind of live on both atoms at the same time. It's not a big concept. We all share lots of things. We all share like our homes with like our families and whatnot. So that's what electrons do. They share orbitals with each other. It's pretty easy. So here's the thing. For it to be a covalent bond, the electronegativity difference must be less than 1.7. That's how we know that we are in the category of covalent. Does that make sense? And what happens, like the reason why it is covalent is because neither atom pulls strong enough to take an electron. So in that tug of war, nobody wins, okay? And what that means is that atoms are shared. That's the thing about covalent bonds, is that they are shared. Now, if they're sharing, if there's one electron that's being shared, it counts on both atoms because it literally lives in both orbitals kind of like at the same time. And so they will do that, like they share, so that each atom has 8 valence electrons, including the ones that are shared. And that's like an important part to remember, is that it has to be including the parts that are shared. Oh shoot! Oh, I forgot to tell you that the magic word is purple. Oh, there we go. Okay. So like I said, 8 valence electrons each. And usually when we have covalent, it's usually nonmetals that are going to be stuck together, right? And the reason why it's usually nonmetals is because they're all kind of clustered together in the same area on the periodic table, and they all have relatively high electronegativities, so nobody ends up winning. They just end up sharing electrons. And so we have a special name to denote that something is held together with covalent bonds, because covalently bonded things behave wildly different than ionically bonded things, and that is this word right here, molecule. The word molecule literally means formed by covalent bonds, okay? So anytime, like for example, when we hear the word atom, that means neutral, right? If we use ion, there's a charge. The word molecule means covalent. That's what that word means, okay? Oh, and also one other weird thing is that hydrogen, so hydrogen's weird, man. Hydrogen is not like all the other elements. Hydrogen and helium are kind of weird, and they're weird because it's just so incredibly small that in a covalent bond, hydrogen we treat like it's a metal. So it'll always be on the left-hand side. It's going to be the one that like has the lower electronegativity. Not that that means anything terribly much for us, just that usually hydrogen will be written first if it's in a covalent bond. Usually, but of course, not always. Because why would anything be simple? And nothing's simple. Not in life, not in humanity, not in the people world, not in the atomic world. Because look, atoms do not always share equally. Neither do you. I mean, anybody with a brother or a sister knows that you guys, humans, we do not share things equally. Neither do atoms. Of course not. And we know that they don't share equally if they have different electronegativities, right? So if something has a stronger electronegativity, right, but the difference isn't quite 1.7, the dude who has the stronger electronegativity is going to kind of hog the electrons a little bit, and whatever has the lower electronegativity is going to like lose the electrons a little bit. So the sharing isn't quite equal. So when the electron lives between both atoms, it kind of spends more time over on one than it does the other. At least that's a good way to think about it. You guys dig what I'm saying? I'm sure you do. So when they're not shared equally, we get this pretty trippy thing called polarity. The bonds become polar, okay? So when they're not shared equally, the bonds become polar. And what that means is that they're, well, not shared equally. And if they're not being shared equally, so if electrons are not being shared equally, let me follow this. That means that they're probably spending more time over with one atom than they are the other. And if electrons are over there more often than they're over on this side, that means that that side's probably going to be a little more negative. And what do you know? That's exactly what happens. So during this tug of war, right? So chlorine, so if you look at this, I have this in here on purpose because you see chlorine, it's a tug of war. Man, chlorine's pulling both those electrons way more over to his side. Hydrogen's still holding on, but it's not really doing that hot. And that's what we get when we get polar. It literally means that one side is slightly negatively charged and one side is slightly positively charged. And this is caused by the electrons kind of living more on one side than the other, okay? And so here, let me do a thing. Like, let's do an electronegativity equals, I don't know, let's do an electronegativity of 2. All right, that's this atom. There's the nucleus. And this atom over here has an electronegativity of 0.5. So the difference between these two is going to be 1.5, right? So the electronegativity difference, so we are definitely going to be covalent, right? However, do you see how this one has an electronegativity of 2 and this dude is only 0.5? So what that means is when the clouds come together, if they were shared perfectly, the clouds would just be like this. The electrons would be like all over the place, right? Problem is that is not the case. This is not what happens. It does not make a nice geometric blob. What happens is the electrons spend way more time over here than they do over here, right? They like to be over here a lot more than they do over here because this side has a much stronger pull on them. So they come over here, but not too much. They spend a lot more time doing whatever they do over here. And you can see what sort of happens is that like this whole thing becomes like blobbed over to one side way more than it does the other. And what that does is it causes a slightly, that's a Greek or something symbol. That symbol means slightly negative. So it's not a full negative charge, but it's a little bit. And if you can see, because the electrons are more over on like that side, that this side becomes a little bit positive because that cloud is shifted in this direction, kind of exposing this nucleus a little bit more. You guys dig what I'm saying? So that is what polar means. It's where one side is slightly negative and the other side is slightly positive. And it's because of the unequal sharing of electrons causing the electron distribution to be unbalanced. Now the electron distribution just means the cloud. The electron distribution is cloud. So let's go with nonpolar covalent bonds because that literally sets us up with two ways that things can be shared. They can be shared equally or they can be shared not equally. So let's get the easy stuff out of the way first. Bam, nonpolar. So if it's nonpolar covalent, that means they are shared exactly equal. The only way this can happen is if the electronegativity of the atoms is exactly equal. It's usually the same element, but it doesn't have to be. There are a few elements that have the exact same electronegativity, and when they come together, they have this thing called a nonpolar covalent bond. Okay, so remember now, ionic is just ionic. There's only one kind of ionic bond. It's just ionic. But when it comes to covalent, there are now two categories. It's polar and it's nonpolar, right? And nonpolar means that it's shared exactly equal, and when that happens, this cloud, can you see how this cloud right here is like shared perfectly? It's perfectly geometric. It's the same on both sides. I'm not really drawing all that well, but you know, freehand. It's also fuzzy, cloudy stuff here, so bear with me. the cloud is even on both sides. Did I spell that right? I don't know. Dyslexics untie or something. So that's what nonpolar covalent means. Nonpolar means it's not lopsided, so it's perfectly equal. Covalent, shared. So this means that they're sharing perfectly equal. That's nonpolar covalent. That's it. And that's all there is to that one. So that's why I wanted to start there, because it's going to get spicy right now. Because let's head over to polar covalent. Now, polar, if you remember, right, not equal, and covalent means shared. So that means they're not shared equally. It's right there. Oh my gosh, it's like it's right in the name. So polar covalent means that they are shared, but they are not shared equally. And this is this is because you have different elements, although it's not all the time, not every single time, because like I just said, some elements have the same electronegativity, so you always do. That's why we have table S, man, because nobody's going to remember this. Just look it up. Bam, there it is. That's how you know. Again, it's caused by a difference in electronegativity that is less than 1.7, but one has a greater electronegativity than the other. And that means that the electrons are going to be pulled to one side and that the bond has slightly positive and negative ends. Now, in this case, I wrote hydrogen and oxygen. Now, I'm not really sure. Let me double check here. So, according to table S, hydrogen has an electronegativity of 2.2. That seems like respectable. It's like right in the middle. It goes from like 0 to 4. But oxygen has, right there, 3.4. So the electronegativities are 2.2 for hydrogen, 3.4 for oxygen. So what that means is oxygen has a stronger pull on the electrons. So it literally pulls all the electrons over to the oxygen side. Excuse me. Do you guys understand what I'm saying? I hope you understand what I'm saying. It's just like you guys sharing stuff with your siblings. The one that's stronger is the one that takes it more often. It's the way it worked when I was a kid. All right, are we good? So, ionic is ionic. 1.7 or greater, electrons transferred. If the electronegativity difference is less than 1.7, now we have covalent. But covalent has two categories, polar and nonpolar. Now, nonpolar is easy. Nonpolar, it's just perfectly equal. There's no polarity. We used the word polarity because it came from poles of like a magnet, so North Pole, South Pole, they stick and stuff. Well, these things stick too. So polar means they're not shared equally. Nonpolar, they're shared equally. Two kinds of covalent bonds. Oh my gosh. So here's the thing. As we start drawing these molecules, I'm going to come back here before. So we're going to go into Lewis electron dot diagrams. But before I go into that, I want to re-emphasize why this is just so super duper important. Because this means that the bond between hydrogen and oxygen, there's one bond between these guys, okay? But that bond is lopsided. And that lopsidedness is the key to like so many like natural phenomenon and chemical reactions and just weird things that happen. It's really important to lock into that. And the Lewis electron dot diagrams are important to show us how those bonds shape the entire molecule. Okay? So, Lewis electron dot diagrams and bonds, they show where and how electrons are shared and the shape of compounds. This is important. It shows us the shape of compounds. I cannot express to you how important it is to have the shape. Reason being, structure determines function. Like your car key is your car key because it's shaped like your car key. If it was shaped like a ring, it would be a ring. Do you understand what I'm saying? It's just that basic, but also important. So, electrons between atoms indicate sharing, and this is important too. You must have 2 electrons for each covalent bond. You must have 2. One bond is made from 2 electrons. And it's almost always 1 electron from each atom, because that's what's fair. It's hard to get these things to share when like one atom doesn't have one and the other does. It's just easier to think of it like they each have to put some kind of money in the basket to share, right? So it has to be 1 electron each. So one bond is made of 2 electrons. You got that? One bond is made of 2 electrons. So The way that we show sharing is we put electrons between the atoms. So here is a carbon, right? This is a carbon, and let's do red for this guy. 1, 2, 3, 4 for that guy, and let's do 1, 2, 3, 4 for that guy. So it's carbon. This one's carbon, this one's carbon. It's going to be like a nonpolar covalent bond. And to show it, we have one from the blue guy, one from the red guy, and we put them right in between. And that's how we draw. That's how we draw that. Now, another way to draw this, just to make it easier, is there's your carbon. Now, the carbon on the left has 3 electrons that are not bonded, so we call those unpaired electrons. And in the middle, we have a bond. Well, instead of drawing so many dots, we just draw a line. And that represents one bond between 2 carbons. And this guy has 3 also. So what does that line represent? That line represents one bond made from how many electrons? Made from 2 electrons. Got it? Awesome. Now that line is going to be really nice, like that shorthand, because once you start drawing these things, like this is just one bond and 2 atoms. You get something with like 7 or 8 atoms. It's like, ugh, you can go crazy with all the dots floating around. It's really cumbersome. So like when, for example, the double bond, now what we're doing is we're taking like this one and this one from each, and now we're making a double bond. So this one and this one, so those 2 from the blue carbon are being shared with this electron and this electron from the red carbon. And now we have 2 bonds, or a double bond. And what that looks like is we're going to draw carbon, and this carbon has 2 valence electrons, and there's one bond, there's the other bond. I will draw 2 lines in between these. See? So it'll look like that. So it's a lot nicer instead of drawing 4, because then you get into a triple bond, and that's just silly. So the triple bond looks like this when we use the line. And that's just too much, man. That gets messy really fast. So we like to use lines instead. So here are the questions that we need to answer. Oh my gosh, so challenging. For the following things, combination of atoms there, we need to answer these questions. Are the following bonds ionic or covalent? That is always the first thing you should do when you see 2 elements and like, okay, bond these together, make a compound first. Is it going to be ionic or is it going to be covalent, right? Now, if it's covalent, you can't just say covalent because there's 2 flavors of covalent. You got to tell me, are they polar or are they going to be nonpolar? Bonds, at least, because like right now we're looking at the bonds. And then I want us to draw Lewis electron dot diagrams for each bond. Got it? And I might not use dots and pluses. I'll probably just use different colors. So first of all, here we go. Type of bond, hydrogen and carbon. Well, how do we know if it's going to be ionic, covalent, or polar and nonpolar? I'll tell you what. I'm going to go table S. I'm going to see that the electronegativity for hydrogen is going to be 2.2, and for carbon, it is 2.6. So my difference in electronegativity equals 0.4. Covalent. Now, what flavor of covalent? Are these 2 electronegativities perfectly equal? Nope, so it's going to be polar. See how that worked? I went to table S. I got the electronegativities for each element, and I used subtraction to find the difference. In this case, the difference is 0.4 covalent, but specifically polar covalent. So these bonds are going to be slightly polar covalent. Now the diagram, here's what we're going to do. Whatever is most ionic, has the strongest electronegativity, is going to be in the middle, right? So I'm going to draw carbon. Now carbon has 4 valence electrons. So what I want to do is draw a compound of hydrogen and carbon. Now hydrogen looks like this. It's got 1 valence electron. Now remember, to make a bond, you need 1 electron from each to get 2 electrons into 1 bond. So here's 1 for hydrogen, here's 1 for carbon. Where do you think this hydrogen is going to go on this carbon? And I think you answered that correctly. Like anywhere there's, like right, so I'm going to go like right here. I'm going to make two electrons into 1 bond. Now the question is carbon happy? Does carbon have its 8 valence electrons? No. No, so the only thing we can do is add another hydrogen. But where could we possibly add another hydrogen? How about over here, right? Here's an unpaired electron. So if we brought in another hydrogen, we could go like that and make another bond. It seems like we're going to need more than just one hydrogen to make this work. Because remember, they all got to do this until they get 8. Except for hydrogen and helium, because they're weird. Right? So this carbon, is it done? Let's check. Is this carbon happy? So this carbon has 2 electrons here. It's 2, 3, 4, 5, 6. A total of 6 outer electrons. Nope. So we're just going to go ahead and put one more hydrogen here. That'll make 7. 2, 4, 6, 7, 8. That's what it'll look like when carbon bonds to hydrogen, right? 1 carbon. Apparently we needed 4 hydrogens for that one. So there you go. All right. You want to move on? I do. Let's come back up to here. Let's go to a different color. Let's go blue for this one. So we got calcium and we got chlorine. So what I'm going to have to do is I'm going to have to go to table S, and I'm going to have to look up calcium, and I'm going to have to look up chlorine. Calcium is 1.0, and chlorine is 3.2. So the difference in the electronegativity is equal to 2.2. This is going to be ionic. What? All right. So, ionic. Let's draw a diagram here. You want to? I know I do. All right, I'm going to need to edit this up a little bit so I can clean it out for us. So it's going to be ionic. So I'm just going to draw calcium right here. Then I'm going to draw chlorine right here. And I'm going to come back to my periodic table so I can find out the number of valence electrons on each. Well, it turns out the calcium has 2. I'm going to put them, I don't know, right there and there. Chlorine has 7. So it goes 1, 2, 3, 4, 5, 6, 7. Okay, now, chlorine, wait, let me go like this. We can go again. Now, chlorine has an electronegativity of 3.2, calcium 1. Chlorine's a nonmetal. Calcium is a metal. You see where electrons are going here, right? So what I'm going to do is I'm going to transfer one of these electrons, and I'm going to move it over here to this here chlorine. Bam! Now let's see if that chlorine is happy. 1, 2, 3, 4, 5, 6, 7, 8. Oh! Lockdown. -1. Ooh, it's so happy, that chlorine. Ah! It's so happy. Let's look at this calcium here. So calcium has a charge of +1. Did it lose all of its outer valence electrons to show that sexy, beautiful 8 shown underneath? No, calcium is not at all happy. It still has, dude, it's got to get rid of that. So how could calcium, you can't just stop right there, because calcium doesn't have its magical 8, and nature be like, no, you go until everybody has 8. That's what nature says. You go until everybody has 8. So you got to keep going. What is the only way you can keep going? Well, when we were over here with this guy, I was all like, well, let's bring in another hydrogen. Well, would it help to bring in another calcium? No. Will it help to bring in another chlorine? Yism. So let's bring in another chlorine. And I'm going to put it over here on this side. I don't want to put a chlorine over here because this is already negatively charged. It's not going to snap two things that are negatively charged together. But if this has a charge, I know it'll stick here. So let's do it again. Chlorine with 7. 1, 2, 3, 4, 5, 6, 7. All right. Just like before, this electron is going to move away from the calcium and go into the chlorine. Chlorine's got 8. It goes into lockdown. Boom. -1. The calcium has lost its second, so it is now a -2. Let's double check everything. This chlorine has 1, 2, 3, 4, 5, 6, 7, 8. It is super happy. Lockdown. Magical 8. The calcium, it has lost all of its valence electrons. It's got 8 underneath, guaranteed. It's super duper happy. This chlorine, 8 valence electrons. Great. It seems like everything's happy. The last thing we got to check is the amount of charge. So everybody has 8. I bet you the charges will work out. Well, I have a -1 here, and a +2, and a -1. So -1, -1, +2, 0, done. That was amazing. I can't believe we just did that. That's like some stuff. Like that's really impressive. You want to do it again? I kind of do. All right, let's go with this one. Silver and chlorine. Only here, I'm gonna clean up all this mess down here. I hope you wrote that down. somewhere on a piece of paper. Because here's what's coming up. Next is silver and chlorine. What color do you guys want to do for this one? Let's do purps. So silver, I don't even know where silver is. All right, oh, I just had chlorine. It's 3.2. Maybe I'll write that. Since I'm here, I remember hydrogen's 2.2. I'll keep that down there. Silver. Yeah, you know, sometimes you just got to suffer through and try to figure this stuff out. And, you know, oh, there it is. Silver, Ag, 1.9. You might want to pause it. Dude, look at that. I had no idea. I did not expect that. I'm not going to lie. I did not. It was a metal and a non-metal, and I was really, really expecting that to be like ionic. But it turns out that this is going to be polar covalent. That's weird. Didn't expect that. All right. That doesn't matter. Nature's not here to like make me feel good about myself, so let's just move on. So silver, I do not know how many valence electrons silver has, but I'm sure this thing does. Oh, it does. It has 1 valence electron. So down here, I'm going to do Ag for silver, and there's my 1 valence electron. And here's chlorine. It's going to go Cl, and I'm going to draw this so that the 1 electrons match up. I'm going to go 1, 2, 3, 4, 5, 6, 7 valence electrons for chlorine, and if it's going to be covalent, 1 electron each. Bam. That's all you can do because all of silver's valence electrons are done. It's shared. It's over. I will never ask you this on a quiz, though, because everyone's going to be like, well, silver doesn't have 8 valence electrons, and my response will be, yeah, because it's a transition metal. But for bonding, it still does the exact same rules, and you may actually see a question like, because these all came from the Regents. It doesn't matter, like all those things, like if it's not following the octet rule, it is, but we just can't see it because it's a transition metal. But they just want you to see that like it's going to be a covalent bond, and so it takes 2 electrons each. You can only make 1 bond. That's it. Okay, that's what they mean for that one. So let's move on. The next one is hydrogen, and I just looked it up a minute ago that hydrogen is 2.2, and the other hydrogen is 2.2. So if the electronegativity difference, the difference in electronegativity equals 0, ooh, one of the rare ones. That one's this is weird. Non-polar covalent. And so this one's going to be super easy. I'm just going to do hydrogen. It's got 1 valence electron. There's hydrogen. I've got my 2nd valence electron. It takes 2 electrons each. Oh, total 1 each. My bad. I said that wrong. It takes 1 electron each, 2 electrons total. Forgive me. And there you go. Bam. Shared. Done. Over. Let's do the next one. All right, so I took the liberty of looking up some electronegativities, and the difference between 2.6 and 3.4, what was that, 0.8? Yep, that is going to be covalent, but they're not equal, so it's going to be polar covalent because they're not being shared equally. And now for this diagram, let's drop down here, and it looks like oxygen might be in the middle. I'm not really sure, so I'm just going to go like this. First, I'm going to draw a carbon over here, and then I know carbon has 4 valence electrons. And then I'm going to draw an oxygen, but so I'm going to put an oxygen right here, and I'm going to try to get the electrons to line up, I hope. So I'm going to go 1, 2, 3, 4, 5, 6. How do I know that oxygen has 6 valence electrons? You already know. You look it up on the tables, one on the end. So remember, it takes 2 electrons, 1 electron from each atom to make a bond. So here's one of the things I do when things get complicated. Like this is where things are going to start to get complicated. I get my eraser. You see I'm pointing in my screen at the eraser that I'm wiggling around here. And I'm just going to erase 2 electrons and then draw in 1 bond. So here is 1 electron from the carbon, 1 from the oxygen. It's like they're both right there. So I'm going to take these 2, right? I'm going to erase them, and then I will draw in a bond. Now let's double check and see if everybody's happy. Oxygen has 1, 2, 3, 4, 5, 6, 7. Oxygen is not happy. Carbon 1, 2, 3, 4, 5. Yeah, nobody's happy. And you can see because there's still leftover electrons. So what I'm going to do is, and we can do this because you have to remember this is a drawing of a three-dimensional object that can twist and move and spin in space and whatnot. So just because it looks like this doesn't mean that's the way it actually is. So I need to take 2 electrons, one from each atom, to make another bond. So why don't I just take this one from oxygen, and which other one you want to take from carbon? I lean towards this one because it's like kind of close and convenient. So I'll take that one too. And those 2 electrons make a bond. So let's double check, see if everybody's happy. Oxygen has 1, 2, 3, 4, because remember each bond is 2, 5, 6, 7, 8. So this oxygen is done. Let's check out carbon. 1, 2, 3, 4, 5, 6. Not happening. So what can we do? Like, do we add another carbon? No, we're gonna add another oxygen. Because that's the other one, right? So 1, 2, 3, 4, 5, 6. I don't know if you caught that, but I went in the other direction just so I could have some line up here. It just makes it easier when I draw it that way. Because remember, this, if my thumb, for you, I don't know, like, right, it's on this side. Now look. Now my thumb is on the other side. It's just facing the opposite direction. Same thing, it's just a matter of perspective, right? So for oxygens, if the single electrons are here versus here, it's just writing it like frontwards versus backwards or whatever. Perspective. It's all relative. It's not science fault. Okay, so one electron from each makes one chemical bond. Neither of them are happy, so I still need to take 1 electron from each and then draw 1 chemical bond. And since there are no valence electrons left anywhere, let's count everybody up. 1, 2, 3, 4, 5, 6, 7, 8. That oxygen is like really super happy. So let's count up for the carbon. So when I'm counting for the carbon, this will be 1, 2, 3, 4, 5, 6, 7, 8. That carbon is super duper happy. Now let's count up for this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Everybody's happy. Whoa. One more and then we'll be done, guys. This last one is going to be sodium and fluorine. And 0.9 and 4.0 to 4.0 is like ridiculously powerful. This is going to be ionic. Like really easy. And because it's ionic, it's going to be easy. I'm going to write sodium with its 1 valence electron. And then I'm going to write fluorine with its 7. All right? And because it's ionic, we're going to transfer the electrons. The metals will lose. The nonmetals will gain. And since it's going to be ionic, do you see how if I just left it like this, that now means covalent, right? But it's not. It's ionic. So we got to lock these in. These have to be locked into the fluorine. And we got to say that it's a -1, right? Not only are they locked in, it's got a charge of -1. And this sodium has lost one of them, so it's going to be a +1. Got to have those charges when it's an ion, okay? So +1 and -1. Bam! Dude, that is a lot of knowledge to be dropped on you all in one time. Whew. The work for these is going to be covalent bonds and bond type. We're going to play around with covalent bonds, like how they happen, and then you're going to get a whole list of pairs of elements, and I need you to determine if it's going to be ionic or covalent. But you can't just say covalent. It has to be polar covalent or non-polar covalent. Holy cow. Whew, that was a lot of knowledge. You guys are going to be like freaking smart by the end of the year. I tell you what. Have a great day, dude.